We're always told that the quantum world is just fundamentally bizarre, a place where reality itself seems to bend its own rules. But what if that's not the whole story? What if the universe is actually a lot more straightforward, a lot more intuitive than we've ever been led to believe?
So let's just dive right in with a really provocative question. What if all that famous quantum weirdness is just an illusion, a misunderstanding that comes from looking at the universe in the wrong way?
There's an alternative view out there that proposes a pretty radical rethink. It says, hey, let's get rid of the whole idea that an observer creates reality. Let's toss out spooky action at a distance. Let's even question the idea of fundamental uncertainty. And what are we left with? A universe that's not governed by mystery, but by simple physical interactions in a physical medium.
So how is that even possible? Well, it all starts by rethinking the most fundamental thing imaginable: empty space. This model says the vacuum, the nothing between everything, isn't nothing at all.
And here is the core difference. On one side, you've got the standard view, which treats the vacuum like an empty, mathematical stage where the play happens. But on the other side, this hydrodynamic view sees it as a physical, granular thing, almost like a fluid, with real, tangible properties.
And this brings us to the big idea. If the vacuum really is a fluid, then all those weird quantum phenomena, they're not magic. They're just the fluid dynamics of the vacuum itself. The ripples, the waves, the little vortices in the very fabric of space.
Okay, so if this idea is going to hold any water, it needs to do more than just sound cool. It's gotta solve problems. So let's see how it squares up against the most famous paradoxes in the quantum world.
First up, the big one. The Heisenberg uncertainty principle. That's the rule that says you can't know a particle's exact position and momentum at the same time. Well, this model completely reframes it. It's not some deep philosophical mystery, it's just a physical limit. Think of it like trying to see details smaller than a single pixel on a computer screen. Space itself is pixelated.
And this model gives a physical cause for both parts of that uncertainty. The uncertainty in position, well, that comes from the finite grain size of the vacuum, that pixel we just talked about. And the uncertainty in momentum, that's caused by the tiny constant thermal jiggling of those grains, giving everything a little kick.
So what about the famous double-slit experiment, where a single particle acts like a wave and seems to go through two places at once? Standard quantum mechanics explains this with a weird idea called superposition. But the hydrodynamic view gives us something we can actually picture. The particle creates a physical wave in the vacuum and then literally surfs it.
Okay, let's walk through this because it's pretty cool. Imagine the particle is like a little knot moving through this fluid. As it moves, it generates a physical bow wave ahead of it. Now, that wave goes through both slits and interferes with itself on the other side. This creates a pattern of high and low pressure. The particle itself, it only goes through one slit, but then it gets guided by that pressure map, naturally surfing into one of the calm, low pressure zones. No superposition, no weirdness.
But now for the biggest challenge of all: entanglement. This is what Einstein called spooky action at a distance. It's the idea that you can link two particles so that measuring one instantly affects the other, even if they're on opposite sides of the universe. It seems to break the cosmic speed limit, the speed of light.
The hydrodynamic solution to this is, well, it's pretty mind-bending. It says entangled particles aren't two separate things at all. They're actually just the two ends of a single object, a kind of flux tube that's taking a shortcut through a higher physical dimension.
The easiest way to picture this is to think of an incredibly long, perfectly rigid rod. If you push one end, the other end moves at the exact same time, right? There's no signal that has to travel down the rod. The whole thing just moves as one object. The two ends are just different parts of the same thing.
So let's put these two ideas side by side. The standard view suggests some kind of non-local, almost magical connection. But the hydrodynamic view says, nope, you're just measuring two ends of the same physical object. No signal is traveling faster than light because no signal needs to travel at all. The object's state is just constrained by its own shape.
Okay, so this is a fascinating story, right? But what separates real science from just a cool philosophical idea? It has to be testable. And this is where the theory gets really daring. It makes a prediction that could prove the whole thing is completely wrong.
And here it is. The core prediction is that this physical flux tube connecting two entangled particles isn't just a mathematical idea. It has a tiny, but very real, physical mass.
And we're not talking about some vague concept. They actually put a number on it. For particles entangled over 1,000 kilometers, say in a satellite experiment,
That connecting tube should have an effective mass of around 10 to the minus 18 kilograms. Now, to put that in perspective, that's about 1,000 times the mass of a single electron. So it's tiny, but it's not nothing.
So how on earth would you even test for something like that? Well, the proposed experiment would look for a very, very small gravitational anomaly. Scientists would entangle large groups of atoms and then use incredibly sensitive gravimeters to listen for a tiny gravitational pull along the line connecting them, the telltale sign of that flux tube's mass. And this, right here, is what makes it real science. You see, unlike a lot of other interpretations of quantum mechanics, this one isn't just a story. By predicting a physical mass, it puts its neck on the chopping block. If scientists look for that gravitational pull and it isn't there, the theory is wrong. And that ability to be proven false is what separates science from speculation.
So let's just zoom out for a second and think about the implications. If this model turns out to be even partially right, it gives us a totally new perspective on our universe, a reality made not of abstract probabilities, but of physical ripples in a universal fluid.
So, to recap the big ideas, if the vacuum is a fluid, then uncertainty is just the pixelation of space. Wave-particle duality is just a particle surfing its own wave. Entanglement is a physical link through a higher dimension. And the act of measurement isn't some strange metaphysical event. It's just you physically disrupting the fluid.
In the end, whether this theory is proven right or wrong, it forces us to ask a really powerful question. Is the universe fundamentally weird, or have we just been missing the bigger picture? It offers a tangible, physical, and deeply intuitive way to see the world. And it leaves us with one last thought to chew on. If reality truly is a fluid, what kind of waves are we?